topic we'll be dealing with today is determining the synchronous generator parameters. Now, last week we saw that the equivalent circuit for a three-phase synchronous generator looks like that. To make it simpler, instead of having the three armature windings, we will only use one set. So we'll be using, this is a per phase equivalent circuit. And it's the circuit we'll be using throughout the discussion today. So as we had said last time, the three-phase synchronous generator consists of the field windings, or the field part of the motor mounted on the rotor, and the armature, which is on this side. So we have stator and rotor. All right. Rotor is supplied with a DC field current, which determines how much flux will be available within the stator. As the DC or the rotor windings are rotated within the space of the motor, you will then find that an induced EMF will be induced on the stator side in all three windings. Remember, this is a per phase, so each of these windings, or rather there will be three of these windings within the stator. So the induced EMF within the stator is determined by those parameters that we saw. K is the construction of the motor itself, or the construction of the windings, armature windings. Phi is the flux, the magnetic field, and omega is the speed at which the rotor is rotated. So phi, as we had said, is directly proportional to the field current that is applied, which is why we have the adjustments, the adjuster resistor that is on the rotor, on the field exciter, right? So now, on the field exciter, we know the parameters that are there. So we know how much voltage we are putting in, we know how much current we can put in. This would be very easily done by having an ammeter connected to the supply. You would then have various elements that you need to determine. So we would want to determine the induced voltage, you'd want to determine the synchronous reactance, and you also want to determine your armature resistance. In the case of the induced voltage, you already know the speed at which the motor is being run, but you don't necessarily know the flux. But to some extent, you can determine how much the flux is, because flux is proportional to the field current. So in this case, you will then have three things that we want to determine, right? So number one is a relationship between a field current and induced voltage. Number two, you will then have synchronous reactance, which is XS, and number three, the third element, armature resistance, right? So the armature resistance straight away is the most straightforward to determine, in that when you have your armature resistance, if you have your three windings, say for example, let's take your armature windings as indicated like that. Let's say they are connected in star. You have your R, Y, and P windings. In order for you to determine the armature resistance is simply the resistance of the coils or the windings that are used to make up the alternator or the armature. So that would be very simple, in that you would simply connect two of them in a star configuration, and you would assume that is RA, that is RA. And if you have a voltage supply, if you know the current that is flowing through and the voltage that you have supplied, it would be fairly straightforward to say that 2RA, because you have connected two of them together, is equal to voltage over the current. whatever voltage you put in as a test voltage will give you the current that you can measure using, say, an ammeter, if you add it inside there. Yeah, and that would be able to give you the values of the windings. Usually, because machines are designed to be balanced, it is safe to assume that RA will be the same for all three sets of windings. So any two of them would give you a good average armature resistance. So that is pretty straightforward. Straight away, you can determine whatever is here in this circuit. So that's parameter number one. We still need EA and we still need XS. All right. The reason why we don't need terminal voltage and the armature current, these are externally measurable from the machine. These are connected to the outside world. Here we are looking for parameters that we do not directly have access to because they are inside the machine, right? And XS, as we said, synchronous reactance, is dependent on the operation of the machine, how the machine is running. So let's start with the relationship between field current, IF, and magnetic flux, phi. So in the case of the three-phase generator, you will have a relationship that looks like that, right? Remember, your VT here is your terminal voltage as measured on the outside, all right? Here it is indicated V phi, but it can also be called VT, okay? That is your terminal voltage measured from the outside, and we want to see what is the relationship of that terminal voltage to the field current or the exciter current that we are applying, this DC current that we are putting here. What's the relationship between the two? Now, remember, this can be found in that VT is equal to EA minus JIA XS and minus IA RA, right? So to some extent, VT and EA have a relationship with each other, barring the effects of these ones. So there's a direct relationship between the two. But we also know that, of course, EA is equal to K phi omega. And in turn, we know that phi is proportional to IF. So phi leads us to, the field current leads us to phi, which leads us to EA, which leads us to VT, which means that this relationship here is very similar to the relationship we saw in the last lecture between the induced voltage or the magnetic flux that is created and the field current that we have, right? So as the field current increases, you see there's a linear relationship up to a certain point. Let's call it that point, okay? Beyond that point, you can see that it tends to now, it deviates from the straight line. This is because of course, the effects of saturation. At some point, there is a maximum amount of current that you can, or there's a maximum amount of magnetic flux that you can induce within the windings of the stator. So any increase in the field current on the rotor side or on the exciter has a limited increase in the amount of magnetic flux that we are creating within the stator. So the usable or the straight line relationship ends at a certain point here, okay? So now those are the relationships between the two of them. Now, in order to test or in order to determine and to obtain this characteristic within test parameters, we would disconnect all loads from the motor. That's number one. Yeah, so that means in order to determine this is a no load test. So that's number one. You're running the motor free of any loads. Number two, you would run, you're running the generator, not the motor, the generator. You would run it at rated speed. So the speed that you would normally run it, usually if it is for main supply, whatever speed would give you 50 hertz is what you run the connector at. And then it would simply be a case of gradually increasing IF starting at 0, from 0 amps, right? So you would be having your generator, no load is connected across, it is open, the windings are just open circuit, there's no load there, but you can measure the terminal voltage even though there's no load, there's a voltage that would appear. On the exciter side, you would start with a 0 IF, and then you would gradually increase it and see the interaction, and you measure the value of the VT, or the terminal voltage, across the terminals themselves, right? Starting from 0 with field current 0, all the way to whatever maximum you would see, at which point you start seeing it deviating like that. Okay, so that's the first test, and that would enable us to determine the relationship between IF and the terminal voltage, right? And this is what we call the open circuit characteristic. Of course, it is open circuit because, as we've said, there are no loads being connected to the terminals. Yeah, it is just an open circuit. So that's the first relationship that we have seen. We don't have any numbers yet, but we already know how the relationship between the terminal voltage and the field are operating. If we were able to get the synchronous reactance and the armature resistance, we can be able to obtain the induced voltage, right? So let's try and obtain now the synchronous reactance. So in order for us now to determine synchronous reactance, we do what is called the short circuit test. So this is short circuit test, right? Of course, that would imply that the terminals are short-circuited to each other. On this side, you have all the terminals short-circuited so that any current that flows through is only flowing through the internal impedances, the synchronous reactance and the armature resistance. Short-circuit those. Once again, we set gradually increase field current from 0 to an acceptable maximum rated current. And that would give you a characteristic that looks like this. So you have on this axis your field current, which you start at 0 and you go increasing until you reach a maximum or rated current. On this axis, we are measuring the armature current, the current that is flowing through the windings of the stator. Yeah, as you short circuit the terminals, you would be able to connect, you connect an ammeter that measures the value of the armature current. So now we have an open circuit characteristic and we have a short circuit characteristic. So how do these help us to obtain the values that we are talking about? Now, when we look at the equivalent circuit, we know that our terminal voltage, let's call it V phi, is equals to internal generated voltage minus JXSIA minus RAIA. If we rearrange that slightly, you get, so you have your voltage and your impedances. Now, in short circuit conditions, such as this one, right? Terminal voltage here will be 0, okay? So this is during short circuit conditions, Vt equals 0, right? So that means 0 is equal to EA minus IARA plus JXS. If we look at that further, we will realize that EA is equal to IA RA plus JXS, and we rearrange that in order to get RA plus JXS is equal to EA over IA. Okay, so this in turn can be able to give us the value, yeah, because we know what the current would be. Yeah, we know what RA was, and you would therefore be able to see what our synchronous impedance is. Okay, whatever voltage is induced, whatever EA is, you'd be able to determine the value of the excess that is inside there. Okay, so that would end up giving us a list of voltages that we can make use of in order to determine the synchronous reactance. So we have got the relationship there, we've got synchronous reactant. And when we combine all three of them together, you can be able to see if we make use of the open circuit characteristic and the short circuit characteristic, superimpose all of them, yeah, superimpose all of them together so that you have your IF on the x-axis and you have a series of points which you can take. At a specific value of IF, you have a value for armature current in the short circuit condition, and you have a value for terminal voltage in the open circuit condition. If you take those two together, you would be able therefore to determine your impedance RA plus JXS, which will be given by VT here over IA here at a specific given value of IF, or at a given excitation under certain conditions. Remember that if you hold the IF constant, your internal induced voltage EA will be the same in both cases. Yeah, but because the two loads are different, that would be able to give you the two loads, meaning you have open circuit or you have short circuit. Short circuit is, you're only looking at the internal loads. The only load that you have is the internal impedances. So that would be able to give us this relationship. And remember, we already found the armature resistance, so that is known. VT at a given value of IF is known. IA at a given value of IF is known from the short circuit. This is from the open circuit. So therefore, you are able to determine the last component, which is JXS. All right. So you have your components now all being able to be determined from your parameters. So using those three tests, you have the DC resistance, which is here, which we used similar to the way we would determine the resistance of any windings of any electrical machine. You have the open circuit characteristic, that is the no load test, and you have the short circuit characteristic when you short circuit the machine. Using all of those, we are then able to determine in turn the resistance and the synchronous reactance. Bear in mind, synchronous reactance is only valid at this particular point. Okay, it is this line that is here, not a point, sorry, at this particular range. Beyond the saturation point, your value of synchronous reactance now changes. You can see it here, right? So it is only, this method is only usable in that range. But generally, you would use your machine, you would use your generator within that range. So let's look at that. Let's say you have an unknown machine. Yeah, it's a 200 kVA, 480 volt, 50 hertz, star connected synchronous generator. Rated field current is given as that. And you carry out a series of tests, the three tests we've talked about: open circuit, short circuit, and then when you apply a DC voltage across the two terminals, the three tests that we talked about. What are the values of armature resistance and approximate synchronous reactance in ohms that would be used in the generator model? So the generator model is what we have here. Okay, so first of all, let's do our resistance test. So resistance test is the way we had said, 2RA is equal to VDC over IDC, which gives us RA is equal to VDC over 2IDC. Let's bring out the calculator. So what's our VDC? It's 10 volts. So RA, 10 volts over 2 times current is 25 amps. So 25. Which is 0.2 ohms, right? So that's your first value, RA. Then let's look at some other valuable measures. So in this case, the internal generated voltage is equal to the terminal voltage in open circuit conditions, right? So here we have, right, at terminal voltage in open circuit, it will be 540. But remember, we are doing a per phase model, so we'll do a bit of conversion. So EA is equal to 540 over root 3, which is given by that 311.77 volts. Okay. Then now we look at short circuit conditions. In the short circuit condition, we can get our IA. So IA, armature current in short circuit, is the same as the load current when we have short circuit conditions, which is given by 300 amps, which was listed here, right? At the rated IF, we have 300 amps. So now how do we combine all those together in order to get our synchronous reactance, which is the last parameter that we are looking for? Okay. So we said that RA plus JXS is equal to EA over IA. EA over IA. Remember, EA was being found from terminal voltage in open circuit conditions, which is there, right? That one here. So we already have a number of these. To make it simpler, let's do the magnitudes. So we will take it as, if we square both sides, then find the square root of the same, we'll be able to get square root of RA plus JXS squared is equal to 311.77 over 300, which is the same as our RA was 0.2 squared plus XS squared is equal to 3. So it is 1.0392. Okay. Let's square both sides so that you have 0.2 squared plus XS squared is equal to 1.3923 squared, which is 1.08. So XS is equal to the square root of 1.08 minus 0.2 squared is 0.04. Okay. Therefore, XS is equal to 1.08 minus 0.04 equal to that. Square root of that is equal to 1.0, let's call it 2. Okay. So in essence, we have determined the circuit parameters of this machine. So EA is 311.77 volts. RA is 0.2 ohms. And the XS, which we have just found, is 1.02 ohms. right? So those are the determining parameters, and we have been able therefore to establish through a simple series of tests how we can determine the two of them. Okay. Now, one thing about synchronous reactance, because it is so much larger than the RA, yeah, 1.02 compared to 0.2. In fact, when we are adding them here or when we are subtracting here, you can see that the difference is very, very small. So for example, if you take the square root of 1.08, square root of 1.08, which is this, yeah, you just take this value by itself, you get a figure that is fairly close to what we are talking about. Okay, it is just near enough. So it can be used to get an approximate value. So what you would determine is, if you want an approximate value of XS, you could take EA over IA. Yeah. In terms of calculations, the value of RA will not make too much difference when you're determining the value of the synchronous reactance, although it may be necessary during other types of calculations. So that's that on the determining of circuit parameters, or finding the equivalent circuit of our synchronous generator.